Evening, everyone.
Evening.
Hello. All right, let's jump right into it. It's our last week of new material, so pat yourselves on the backs, everybody. You've made it this far, and the last week isn't that tough. I think you should be all right, especially if you've got a decent understanding of how, probability works. That's what this is all kind of going to be based on. So as long as you got a basic concept of how it works, you should be fine. We've talked about these before. There's the difference between a continuous variable and a discrete variable. Well, it's going to come into play a lot this week because now we're going to be talking about continuous random variables. So last week when we talked about the binomial distribution and the good old Poisson, the Poisson one, both of those were what are called discrete random variables. So they work off data that is discrete data, counts, you count the number of things. Well, now we're going to be using the normal curve and z-scores, and those are things that are done with continuous random variables, things that are measured. Remember, so discrete is counted, continuous is measured. We've talked about these kinds of examples before, heights and weights and the length of life of a particular product, right? So you can see that the passage of time, right? The length of life of something would be the same thing as your age, right? That's the length of life of you so far, right? So age and any kind of measurement of time is always considered a continuous random variable, even though it's normally reported kind of more discreetly. Okay. So what does it mean to have a continuous random variable and then thus have a continuous random variable distribution? Well, with the binomial distribution, you had all these little individual bars. You basically had a histogram where you had each little bar represented the probability of a certain thing happening. So for instance, if we go to StatCrunch, and we can see that there's a typical binomial distribution where you have the little bars representing the probability of each thing happening, right? So this one defaults to a sample size of 10 with a probability of success being 0.5, right? If we change this to, let's say, 0.25, you'll see how it now is skewed to the right, and it's no longer has a normal shape because of the different probability, but each one of these bars represents the probability of one of these discrete numbers happening, right? Because you can't have anything other than zeros, ones, twos, threes, and fours because you're counting the number of successes. So the probability of getting exactly one success out of 10, right, it's a little less than 20%. And the probability of getting exactly 2 successes out of 10, it looks like it's getting close to about 30%, and so on and so forth. That's a discrete probability distribution. However, once we get a continuous probability distribution, we get these nice, pretty curves that we now shade in regions to represent probabilities, because we can no longer talk about the probability of exactly one thing or exactly two things because there's no area involved, right? So when we do continuous random variables, we're calculating area under a curve, and that area in between 2 points is what defines the probability. So that's why, as I said, we can no longer have the probability that X equals a specific number, right? You can no longer say what's the probability that X equals 5 or X equals 100 or X equals even 247.3, right? It doesn't matter if it's a whole number or not. The probability of that will always be 0, because when we're calculating probabilities for a continuous random variable, we have to find area. And if we're looking for the probability of a precise number, there's no width. And if there's no width, there's no area, right? So you always have to have the probability that X is greater than something, X is less than something, or X is in between something. And there's absolutely no difference between greater than or equal to versus strictly greater than, right? Because the only difference between X being, let's say, greater than or equal to 2 versus X being strictly greater than 2 would be strictly greater than 2 doesn't include the value of X equals 2, but as we just saw, X equals 2 is 0. So there's no difference between a strict inequality of less than or a less than or equals or a greater than equals, right? So those symbols are interchangeable. There's really no reason to use one versus the other.
Dr. McBride.
Yes, sir.
I just have a quick question about the curve. If you have any skewness one way or the other, are we supposed to do something with that? Can we use it that way or?
Great question. So, most of this stuff is a theory, right? Where we're talking about theoretical probabilities, not experimental probabilities. And theoretical probabilities are built on a perfect normal curve. So this perfect bell curve that won't have skewness. Now,
okay.
When you go and have some sort of experiment or you have some sort of actual real set of data that is continuous data, then by all means you could absolutely have data that is skewed, and that's totally fine. When you go to compute a probability, it's still going to compute the probability of being less than a certain amount, greater than a certain amount, or in between a certain amount. And it's going to use the shape of your distribution to calculate those probabilities for you, in technology. Yeah, so it would be fine if you didn't have a normal curve. It's just for the learning of the theory of it, we have to think of it as having a perfect normal distribution.
Okay, gotcha. Thank you.
Yep, good question. All right, so if we're going to deal with these things, with technology, you can, of course, do them very easily in Excel. You can do them extremely easily with a TI graphing calculator, if you have one. You can do it in R, for those of you that use R or SPSS or, StatCrunch and Vassar Stats and probably 1,000 other, things. And then, of course, we can also do it in SAS very easily with the simple CDF normal and PDF normal call outs, quote unquote functions, right? That we have in our how-to, right? Well, here's the binomial stuff from last week and the Poisson stuff. And then here's the normal stuff, the CDF and the PDF. If you just, copy and paste that into SAS, you're good to go. And you can do all these things quick and easy and painlessly in SAS. So all you need to realize is that in the formula, X is the value of interest. It's the number that you're looking for, right? What's the probability that if you pick something at random, it's going to have a measurement that's less than 14? Okay, then X is going to be 14. The U is going to be the mean of your sample, and the S is going to be the standard deviation of your sample. And it's fairly similar context if you were going to do it here in Excel. Let me make this bigger so you can see what it's doing. So you could do equals normal dot distribution, and you can see it tells you what it's looking for. It wants X first, then the mean, then the standard deviation. Then you tell it whether or not it's cumulative. So we can say, okay, here's 14. Let's say the mean was 12 and the standard deviation was 2.3. And then it says true makes it a cumulative distribution and false makes it that the PDF, the probability mass function versus the cumulative one. So if we did, we're always going to be doing cumulatives, right? So we basically want the true. You can just double click on that, or you can type in true. If you click this, that's going to be the probability of being less than or equal to 14, right? Given that the mean was 12 and the standard deviation was 2.3. So basically what that's saying is if we had a our distribution, say our distribution was normal-ish, right? Looked pretty much like a bell curve. The mean is always right here in the middle, right? And I said the mean was 12. And then we were looking for, we put in 14. Is that what it is, or was the mean 14? I put in 12. Yeah, I put X was 14, mean was 12. Okay. So 14, let's say, is about here. And basically the cumulative density function, right? The normal CDF, all it's doing is giving us all of that area. And all of that area represents the probability that X is less than or equal to 14, which is the exact same thing as the probability of X is strictly less than 14, which equals, it was like 0.8 something, wasn't it? 0.077. So we'll put 0.808. Oop, what the hell just happened there? Come back. Oh crap. All right. Just love technology. I'm sure it's gone. Yeah, so the picture's gone, but you get the idea. That's what we're doing with that thing. Okay, the standard normal, right? So the example I gave you, the mean was 12 and the standard deviation was 2.3. And you can have, you know, whatever mean and standard deviation you have based on, you know, whatever your data is. The standard normal is just a normal curve that has been standardized. And basically all that we've done is we've shifted it so that the mean is 0. And then we've normalized the distance that is considered a standard deviation. Instead of it being 2.3 or 4.7 or 0.3 or whatever it happens to be, we make it a 1. So basically the standard normal distribution is still just the same as any other normal distribution. All the same rules apply. The only difference is the mean has now been set to 0 and the standard deviation has been set to 1. And that's the distribution that we use whenever we're calculating or finding what are called z-scores. And z-scores are just fancy ways of saying how many standard deviations you are above or below the mean. So if a piece of data that you pick and then you calculate a z-score for that piece of data, and if that z-score is 1.2, then all that means is that piece of data is exactly 1.2 standard deviations above the mean. And if the z-score comes out to negative 0.3, then it means that data value is exactly 0.3 standard deviations below the mean. That's all a z-score is. It tells you how far a specific piece of data is from the mean in terms of standard deviations. So 2.7 is 2.7 standard deviations above, right? A z-score of 3 is exactly 3 standard deviations above, and so on and so on and so forth, right? So that's all z-scores are. Like I said, negative ones means your value is to the left of the mean. Positive ones means it's to the right of the mean. Something that I've mentioned before, but we'll mention it here again. The total area under any normal curve, not just the standard normal curve, but any normal curve, and really technically the area under any continuous probability distribution. So even that first example that we saw that was nice and skewed, this one, as long as that is a continuous probability distribution, then the area under that curve has to equal 1, because remember, the area under the curve represents probability. And we know that if we sum up the probabilities of all possible outcomes for any kind of experiment, right? So it's called our sample space. Those probabilities will always sum to exactly 1. We talked about the simple values like, you know, if you roll a 6-sided die, there are 6 outcomes. It either comes up as a 0, a 1, a 2, a 3, a 4, a 5, or a 6, right? So the sample space of that experiment would be exactly that, a 0, a 1, a 2, a 3, a 4, or 5, or a 6. And the probabilities of each of those outcomes happens to be 1/6, right? Because we're going to assume that the die is evenly weighted. And when you add up all 6 of those 1/6, right, you get 1. Another simple example, flip a coin. The sample space for flipping a coin is heads or tails, right? That's it. That's the complete sample space. That's the only way that that experiment can come out, right? Those two outcomes. And each of those outcomes just happens to have equal probability of 0.5, and you add them together and you get a probability of 1. Now, that doesn't mean that obviously outcomes always have equal probability. It's just those two examples, right? You could have a coin that was weighted improperly. And there's coins in the real world that are like this, because there's like a really big stamped picture on one side, and it makes the coin weighted more on one side. And so it'll actually not come up heads and tails 50-50. That's actually possible, and it does actually happen in the real world. So you could have a coin that maybe 60% of the time lands tails up, because the picture of the dude on the front is so embossed, right? It's so thick that it throws the center of gravity off, and it tends to fall face down more often than face up. But that one would still have a probability of 60% being tails, 40% being heads, and it would add up to 1. So the area under these curves will always be 1. It just so happens that when we have a perfectly normal curve, we also get that it's perfectly symmetrical. So we get exactly half of it above the mean and half of it below the mean. So here's another pictorial example, right? If we're looking for the probability that something is less than 1.36, we could throw it into our formula. And visually, here's the 1.36, and it's less than that. Now you'll notice that here it's saying z is less than 1.36. So in this case, we're assuming that 1.36 is a z-score. So we're looking for some data value that is less than or equal to 1.36 standard deviations above the mean, right? So it's that far above or less, right? So that's why it's everything below it, right? Less than or equal to 1.36. So when you see z's, it just means that we're doing z-scores, which just means that we're on a perfectly standard normal curve. But it's still the same darn thing. You'll notice that we're still using the formula that's all about x's, right? So x being just the value of interest. And in this case, the value of interest is 1.36, which just happens to have this fancy name of z-score. But it's no different than just having a data value of 1.36, right? Don't let these names throw you off. Oh God, a z-score is totally different from a data value. No, it's not. Same damn thing. It's just a number. That's all it is, right? It's just a z-score happens to have a different kind of connotation to what that number represents. If 1.36 was just a data value, then it would have represented some sort of measurement, right? You took a bunch of measurements of things, and that became your continuous data set. And 1.36 was just one of those measurements. However, now, if you're talking about z-scores, then 1.36 is just a z-score. It's still a measurement, but instead of a measurement that you took in your experiment, it's a measurement of the distance that one of your data values is from the mean in terms of standard deviation. So it's 1.36 standard deviations away from the mean. Think of a standard deviation as just a unit of measure, no different than inches, feet, yards, miles, centimeters, meters, kilometers, right? Those are all just units of measure. So you could be 1 inch away from something, or you could be 1 foot away from something. You could be 1 standard deviation away from something. And that standard deviation just happens to have a value to it. And depending on your set of data, your standard deviation could be 2.3, and my standard deviation could be 5.7. Just like, in olden days, the measurement of a foot differed from place to place because it was based on the length of the foot of the king or monarch who looked over that little serfdom or fiefdom. So you would have different measurements for feet all over Britain, right? Because of that, until it was finally that's not centralized, but unified, right? They just said, okay, a foot's going to be this long, right? So it's the same thing. A standard deviation can differ from here to there and there to there, but it's still just a unit of measure. All right, now if we have to calculate probabilities that are greater than or equal to, remember, because the two are the exact same thing, we still use the same technique, right? We still would put 1.36 in as our X value, because that's our value of interest, right? That's the number of interest. But when we throw that into technology, and it doesn't matter if you're going to use Excel, SAS, R, a TI calculator, whatever, they always default to the standard CDF function, which always accumulates things from the far left-hand side up, right? In the binomial distribution, the farthest left you could go was 0, right? Everything was 0 and above in a binomial because you couldn't count negative things. With a continuous random variable, this distribution all of a sudden now has a negative side and a positive side, because the distribution is now, it's no longer technically representing your data, it's representing these z-scores, which remember are units of measure of distances from the mean. And if you take the average of any set of data, obviously some data values are going to be bigger than it, and some data values are going to be smaller than it. So that's why you're going to have, the negative side of the curve and the positive side of the curve. So with the binomial CDF, it would add up from 0 up to that point. When we're doing these normal CDFs, it goes from basically negative infinity up to that point, right? So it takes all the area from negative infinity up to 1.36, and it adds that area together, and it gives you that probability. So if you want the probability of being bigger than that, bigger than 1.36, you simply just subtract that from 1, because again, we know that the total area adds up to 1, because we know that total of probabilities adds up to 1, right? So if the probability of being to the left of this number is 0.9131, then if you subtract that from 1, that will give you the complement, i.e. the other side of it. And now the probability of being bigger than 1.36 is simply 1 minus that number, which gives us the 0.0869. So that's how we can find aboves. Belows are easy. And if we want to find in-betweens, we just have to do some simple math. Now, if you've got a fancy tool like StatCrunch, it'll do betweens for you, where you just put in the two numbers here, and then it'll calculate betweens for you, which is kind of nice. Excel doesn't do this. You would still have to basically run the CDF twice and then take the difference of the two, just like you would have to do in SAS. So basically what you're doing is you would run a CDF of 1.36, and that will give you the area from this value all the way down to negative infinity. And that's the 9.131. Then you run the CDF on the lower value, right? The lower end, the number on the left of your thing, right? You're trying to go in between these two numbers. So the smaller of the two. Now the smaller doesn't have to be negative, right? This could have been in between two positives, could have been in between two negatives. Just this example happens to be that the low end is on the negative side and the high end on the positive side. Don't think that's always the case. It could be, any combination, just as long as the number on the left is smaller than the number on the right, because otherwise this wouldn't make sense, right? How could something be smaller than, let's say, 1? Or sorry, how could something be bigger than make this positive one, just so it's in your head better. Bigger than 1 and smaller than, negative 2. You're like, wait, that's impossible, right? So they always have to go smaller number on the left, bigger number on the right. But in any case, you do the CDF of the big number, and that gives you the area from the big number all the way down. Then you come back and do the CDF all over again on the smaller number, and that gives you the area to the left of that smaller number. And then you can see graphically, if I subtract away this little tail from the first measurement, it's going to give me the leftover bit in between. And that's literally all you do, right? You take the probability of the bigger number, subtract the probability of the smaller number, and the leftover is the probability of being in between the two. So that's how we do a less than, a greater than, and an in between. Questions on any of that?
So with this one, we don't have to subtract from the 1?
Well, in this example, no, you don't subtract from 1. You only subtract from 1 when you want to do a greater than, because remember the whole thing adds up to 1. So whenever you're trying, the function of, you know, the CDF always gives you area to the left. And since the total area is 1, if you want area to the right, that's why we subtract from 1. With this example, in between, when you run the CDF, it gives you area below, but it gives you all this junk in the tail that you don't need. So that's why you then run the CDF for the tail, which is basically just run it on the lower end, which gives you the tail area. And if you subtract that from your first answer, then it gives you the in-between.
Okay, so can you go back to that other slide that you just came from? So why did we subtract from the top one and the bottom if one was greater than and the other one was less than?
Well, the less than, we didn't do anything. We just got the answer.
So, but if you go to the one that you just showed, not the one, not that one, this one. So you see how
We're subtracting from 1. We're subtracting our answer from 1 to get above.
right, and then at the bottom we did it again, but we subtracted that.
Well,
At the
this
bottom.
is just the example that it's just pointing out the fact that these are complements of each other, right? If we wanted to find the greater than, we would take, it's basically just, it's writing it twice. It's just telling you the same thing.
Okay.
From the previous slide, the probability of being less than 1.36 is 0.9131. So this is just reminding you that that's where that number came from. And then if we take that and subtract it from 1, it's going to give us what we're actually looking for.
Okay.
So it's kind of, I mean, they probably should have put this stuff above to remind you this is what we had. And then now that we do this, so you can just kind of ignore this. This is just showing you where this number came from. Like somebody might go, well, where the hell did 0.9131? Well, I'm just reminding you that it came from the previous slide when we calculated the probability of being less than 1.36. It's just telling you that that's how much area is in this left. This piece over here is 0.9131. All of this.
So when we have two of the equations together like that, so is one of the probabilities subtract from one and the other one we don't?
Well, you only have 3 situations. If you're asked to find a less than, you just run it, and that's it. If you're asked to find a greater than, you run it and subtract from 1. If you're asked to find an in-between, you have to run it on both of the endpoints, right? So you have to run it on both of these numbers and then take the difference of them, the bigger one minus the smaller one.
Okay, so that's what I was talking about. So when it's less than on this one, we don't have to subtract the one of them from one.
No, you never
Okay.
have to subtract from 1 for this example.
Okay, got it. Okay, thank you.
Yep. Now I suggest, guys, rather than trying to memorize when do I do this and when do I do that, just draw a picture. If you draw a simple picture of a distribution each time and shade in what you're looking for, it will help you kind of figure out and remind yourself of what you need to do. And then all you have to remember is that the CDF function, right? This probability CDF function always gives you area to the left of your value. So if I wanted to do an in-between, let me just do a slide. So let's say I wanted to calculate the probability of negative 1.5 is less than X is less than or equal to 2. Right? Remember, it doesn't matter if it's Less thans or less than or equals. That's why I put one of each. So we're going to assume this is a z-score. I probably should have written this as a z so that we're on a standard normal. So here is 0, right? Because the standard normal curve, the mean is always 0. If we want to be in between these two things, we know that we're going to have a little thing, in between here. But let's look at it in terms of colors. So 2 is here. And if we do a CDF of 2, it's going to give us all of this, right? Everything less than 2. That's what we get from a CDF done at 2. It will give us all of that. But that's not what we want. We want this stuff only, right? We only want what's in between the two. Well, if we come along and do a CDF of negative 1.5, that's going to give us this. Because that's what the CDF does. It's always less than or equal to your value. And you can see pictorially, if you take the green stuff, subtract the blue stuff from it, you're going to be left with the black stuff in the middle, which is what you want. Right? So that's an in-between. All right, any other questions? All right, here's another example, same type of thing, right? If we're trying to find between 0.8 and negative 0.85, you'll notice now that in this example, we're no longer doing z-scores. We have just values of 0.8 and 0.85. So it says the weights of packages of ground beef are normally distributed with a mean of 1 and a standard deviation of 0.1. And they want to know what's the probability that if you randomly select a package, it's going to weigh between 0.8 and 0.85 pounds. So this curve, instead of being centered at 0, it's going to be centered at 1 because that's the mean of this distribution. And instead of having a standard deviation of 1, it's going to have a standard deviation of 0.1. Well, that's fine. It doesn't change things. Everything still works the same. If we're looking for the area in between things, we would still have to run this twice. We would run it a CDF on 0.85, which would give us from here all the way down. Then we would run it on 0.8, which would give us a little tail piece. We subtract those two from each other, and we get this answer of a little bit more than 4%. And you'll notice it's kind of hard to see, but over here there's a little X and below it is a little Z. If we wanted to, we could change both of these values into z-scores, and then we would be finding answers back on this normal z curve, the standard normal curve, because we would be dealing with z-scores. So you can take 0.85 and you can plug it into the z-score formula, and it'll say, hey, well, if you have a mean of 1 and a standard deviation of 0.1, then 0.85 actually has an equivalent z-score of negative 1.5. Because remember, a z-score is just how many standard deviations you are below the mean. So look at 0.8. 0.8 is exactly 0.2 below the mean. Well, 0.2 is exactly 2 of these, right? And because it's below, it's negative. So that's why 0.8 would have a z-score of negative 2. 0.85 is exactly 0.15 below the mean, which is 1.5 of these things. So that's why it had a z-score of negative 1.5. So you could always turn them into z-scores and then calculate these things based on z-scores. But why bother? Technology lets you plug in the mean and the standard deviation. So if you want to do it with a z-score, you would make the mean 0 and the standard deviation 1. But then you'd have to go through the hassle of finding z-scores for everything, when instead, screw it. Just put in the mean that you have of 1, the standard deviation you have of 0.1, and then do everything that way and get the same exact answer rather than having to convert things into z-scores. Okay, now this formula is slightly different. This is the quantile function. And what it does is it basically does the CDF function in reverse. So pictorially, remember the CDF function says, you give me a value like 2, and I'll tell you how much area is under the curve to the left of that value. So if you give it the value of negative 1.5, it'll give you all the area to the left of negative 1.5. What the quantile function says is, instead of you giving it a value, you give it a probability. You say, I'm going to give you a probability of 99. I'm going to tell you what the mean and the standard deviation is, and you're going to return a value. So instead of me giving you the value and the function gives me a probability, you give the function a probability and it spits out a value. You see how it's just the inverse function. It just basically goes in the opposite direction. So this is one of those things where instead of wanting to know what's the probability of being below a certain number or above a certain number in between a certain number, this is asking the question, what number do I need to have in order to have a probability of blank, right? So this is basically saying, I want to have 99% of my data below me, because this is just like a CDF, the probability it gives you is always area to the left. So this has 99% of the area below it, which means it only has 1% of the area above it, which means this data value is what we would call the 99th percentile, right? Because a percentile is always how much of the data is below that value. So if we have 99% of the area, right, 0.99 below it, then that means it's got 99% of the data below it, and that means it's in the 99th percentile. So this would basically just be a way of finding the 99th percentile. And if you ran this, it would spit out the answer of 1.23. This 2.33, that's a z-score. 1.23 is the actual answer from the context of this question, where the mean is 1 and the standard deviation is 0.1. So what that means is, if we looked at all packages of ground meat, 99% of them would have a weight of 1.23 pounds or less, right? Because the mean was 1 pound. Well, that kind of makes sense, right? Because manufacturers aren't going to have a huge standard deviation. As you can see, their standard deviation was 1/10 of a pound. So it's going to be pretty rare that you're going to get a package that's going to come down the assembly line, right, the production line, that's going to weigh more than 1.23 pounds when they're trying to only make it weigh a pound, right? Because they're only charging you for a pound, so they surely don't want to give you more than a pound. So it makes sense that 99% of them should be 1.23 or less. So that's the quantile function. It basically just goes in reverse. It says, instead of you give me a number, I give you a percentage, it's you give me a percentage and I tell you what number is that cutoff, right? Has that much percent of the data below it. Okay, questions on the quantile function?
It's not a question on the quantile. Just thinking about those z-scores. I mean, the only reason that you would convert your x's to z's is if the only thing you had with you was your textbook and you needed to use the tables, right?
Yes, or the only other reason why you would do it is so you could compare apples to oranges. If you had
Okay.
if you had two different sets of data that had two different means, right? Two different standard deviations, and you wanted to compare two pieces of data, one from each set, you couldn't do it without z-scores. And in fact, z-scores is what they do for like the SATs and the ACTs. I'm sure you guys are all familiar with those because you probably all took the GRE recently just to get into grad school, right? These standardized tests have scores, but when they report your score, they also report your percentile, and they also report a z-score. Because if you guys aren't familiar with it, the SAT, it keeps changing. The last time I checked, it was on a scale of 2,400. I think they made it 800, 800, and 800 for 3 different. When I took it, it was out of 1,600. You had 800 for math and 800 for English. and your score was based out of 1,600 points. The ACT has never really changed. And it's, when you take it, your score is out of, I think, like 32 points. So if you were a college admissions person and you had one student show up, you know, trying to get into your college, and they had an ACT score of 20, and then this other student showed up and they had an SAT score of, let's say, 1,300. Well, how the hell do you know which one is better than the other, right? Who actually scored better? Because these two tests are on two completely different scales. Well, if you calculated a z-score for each of those, the z-score tells you how that data value relates to the entire set of data, right? So if the z-score for a 1,300 on SAT comes out to be 1.3, then that means they were 1.3 standard deviations above the mean for that test. And then if you look at, I think I said 20 or whatever on the ACT, if that comes out to be 1.4, then that means that score was 1.4 standard deviations above the mean of that test. And it means they actually did better, right? Because 1.4 is bigger than 1.3. They're further to the right, which means they're, you know, they would have a higher percentile score because they would have more stuff below them. So that's the other reason for z-scores, is it allows you to compare apples to oranges, right? It lets you compare scores from two different sets of data that are obviously on two different scales. Make sense?
That makes total sense. Thank you.
Awesome. Great question. Thank you. Anything else? Okay. Pretty much the last thing that we deal with in this chapter, week, section, module, whatever you want to call it, is the idea of doing the normal approximation to the binomial. I've mentioned this before. This is one of those archaic tools that's no longer used. Way back before, you know, we all had basically a supercomputer in our telephone. It was really difficult to calculate binomial probabilities when the sample size was really large, because the formula for a binomial is pretty intense when there are big numbers. I mean, it's a simple formula, but the computations become rather immense with big numbers, right? So it was really difficult to compute a binomial with large numbers. But when you have a large numbered binomial, the bigger the sample size gets. When I say large number, I mean your n, right? So when your experiment involves doing something n number of times, and that n gets bigger and bigger and bigger on a binomial, then what happens is the shape of that binomial gets closer and closer and closer to a normal curve. In fact, if you think about it, as n gets bigger and bigger and bigger, these bars are going to get thinner and thinner and thinner, because you're now going to have to fit more numbers within this same distance. And as they get thinner and thinner and thinner, they basically just turn into little lines, and then they basically fit a normal curve perfectly. And so you can get a really nice approximation to the binomial using a normal curve when n is sufficiently large. And you might ask, okay, well, how sufficiently large does it have to be? Well, the other caveat is that p can't be too close to 0. As you saw before, if you noticed before when we did this, when my p was 0.5, this distribution looks very normal. But as p gets smaller, it starts to get more and more skewed, right? Look at how skewed it is when p is 1. But if you now pump up the n, look at that. It went right back to normal. And you see how it's kind of hard to see, but there's just a crap ton of these little verticals, right? There's a whole bunch of those little vertical, quote unquote, bars showing areas. So this nice relationship between n and p is, as long as their product, right? So if you take n, you multiply it by p, no matter how small p gets, as long as you let n be kind of conversely large, then you will still get a normal shape to your distribution. And so the rule came out after trial and error. We figured out that as long as n times p is sufficiently large, this approximation will hit. Well, what is sufficiently large? If I remember off the top of my head, it's n times b has to be greater than or equal to 10. Don't quote me on that. Double check with your book.
It's 5.
Is this
I
5?
looked it up today. I did the homework. Yeah.
Awesome. Okay, it's 5. Thank you. So as you can see, my memory sucks. So it's 5. You'll also realize that I don't have this memorized because, as I said, this is one of those archaic things that nobody uses in the real world anymore. It's really just a teaching tool at this point. It's really just used to point out the fact that if you have a discrete probability distribution like the binomial, and you let n get really, really big, it's going to morph into a continuous distribution. It's this idea that if you run an experiment more and more times, it's going to become a nice continuous variable. Now, obviously, it doesn't perfectly become it, but it matches it more and more and more the larger it gets. So, like I said, in the past, binomials were hard to compute with large numbers. The normal curve was always really easy to compute because, as some of you have probably found out, there are tables where you can do a z-score and you can look it up in a table. And those tables were, very easy to compute using simple integral calculus, which is something that, the old statisticians could do before they had a calculator very easily with, paper and pencil. So it was always easier to calculate probabilities underneath a normal curve than it was super large binomials. So we would use the normal to approximate the binomial. And then along came computers and, SPSS and SAS and R and TI and all that stuff, and went, oh, look at this. We can now calculate probabilities of binomials for super large n's, and we can get the precise answer. So we no longer need to approximate it with a normal, but it's still kind of cool that we could if we had to. So let's leave it in here as a teaching tool. And that's really all it is. In practice, nobody would ever do this, because why in God's name would you get an approximation when you could actually get the precise answer just as easy, right? You wouldn't. That's silly. But it's just, like I said, a teaching tool. So there is, I believe, one question in the homework where it wants you to do the approximation to the binomial using a normal. There might even be 2. It's 1 or 2 of them. Just do it just to see how good it can be, right? But just know that in real life, you would never, ever, ever do this, because you would just get the precise answer out of the binomial. The other thing to think about is when you are doing these approximations, you have to do this continuity correction. And it's the idea that you're fitting a continuous distribution to a discrete one. So if you're trying to find, the probability of being less than 4 in a binomial sense, well, that means you only want 0 through 3. So you wouldn't set x to be 4 on the continuous spectrum, because then it would count up all the area, including 4, and you only wanted 3 and below. Well, you also wouldn't want to put x at 3, because that would only give you the area basically less than 3, and you want it to include 3. And you're like, okay, well, I can't do 4 and I can't do 3, because 4 gives me everything less than 4, which is, bigger than 3, but x of 3 gives me everything less than 3, which doesn't include 3. It's like, what do I do? Well, you just put 3.5, because then what it does is it gives you enough of the continuous to include the entire bar for 3. Pictorially, what's happening is you have these little bars, right? Each little bar represents the probability of that precise number in a discrete distribution. When you fit the continuous curve over it, the bar is centered on the number, right? So if this last red bar represents the probability of getting a 10 in this experiment, then the right-hand edge of that bar is basically halfway in between the 10 and the 11, which is the next bar. So that edge is at 10.5. So that's why you would set the continuous x for your normal curve at 10.5. And that will give you all of those bars without giving you half of the next one And if you set it at 10, it would cut this bar in half and you would lose half of that last bar that you want. So that's what this continuous or this continuity correction means. It just means you always have to go up by a half or down by a half, depending on, you know, the bars that you're trying to get. If you want to be greater than 4, then you don't want to include 4. You only want to include 5 and above. But the bar for 5 is centered on 5. So the left-hand edge of 5 is down at 4.5. So that's why you would do 4.5. However, if you want to be less than 4, you only want to include the bar that represents 3 and below. The bar that represents 3 is centered on 3. So the upper edge, because remember now we're doing below instead of above, right? The other example we're going above, so we're looking at the lower edge. Now that we're going below, we're looking at the upper edge, and the upper edge for the 3 bar ends at 3.5. So that's why you round up or down, or I shouldn't say round up or down. That's why you add 0.5 or subtract 0.5, right? You go up by a half or down by a half. If that's making your head hurt, then just write this in your notes, guys, and just remind yourself that anytime you're doing a less than, you go half of a point below that number. And anytime you're doing a greater than, you just go half of a value above, right? So it's kind of nice that it's intuitive. Less than, you subtract a half. Greater than, you add a half, okay? And that's how you can get a more accurate approximation using the normal curve when you're trying to approximate the binomial. The last thing you have to remember that in order to do this, you have to find the mean and the standard deviation of your binomial curve so you can plug those in. Because remember the formula, whether you're doing it in Excel or whatever, it needs to know what is the mean and what is the standard deviation for your distribution. And then of course, what's your X value, right? What's your value of interest? So the formulas for both of these are very simple. They're also included in the SAS how-to right here, that n times p is your mean, and then the standard deviation is the square root of npq, where q is just the complement of p, right? So if the probability of a success is 25%, 0.25, then q is literally the complement of 0.75, right? Just 1 minus that. So that's how you calculate these things. N times p gives you the mean, square root of npq gives you the standard deviation. So then you would use this as your mean, this is your standard deviation. You would plug those values in for mean and standard deviation. You would do your continuity correction, and you would use 10.5 because you want to find the value is less than 10, right? So you have to less than or equal to 10. So you have to include 10. Oh, this even goes against this, right? Because look at this, less than was smaller. Now all of a sudden, less than or equal to, it seems like it's bigger. But you have to remind yourself that less than or equal to 10 really means the probability that X is strictly less than 11, right? Because in a binomial distribution, less than or equal to 10 means you include 10 and then everything less than 10. Whereas if you're strictly less than 11, you don't include 11, you just include 10 and below. So those two things mean the exact same thing. This example was with a strictly less than or a strictly greater than, right? So this rule of less than is a half smaller and greater than is a half bigger only works for strictly less than and strictly greater than. So you either have to always change these and then use that memorization, or just draw a picture, like I said, over and over again, and think about it logically, right? Just stop and think through it. If I need to include the bar that represents 10, I have to remember that the 10 bar basically goes from 9.5 to 10.5 because it's centered on 10 and it goes a half in each direction. Because then the next bar for 11 starts at 10.5 and goes to 11.5 and so on and so on and so forth. So if I want to be less than 10, I don't want to include that bar at all. And the low end was 9.5. So I would put 9.5 in and I would run it. But if I want to be less than or equal to 10, then I do want to include the 10 bar. And the 10 bar goes all the way up to 10.5. So now all of a sudden I have to use 10.5 as my X value. And so that's why we use 10.5 in this example. So that's going to be the hardest part about doing these stupid approximations, is figuring out, do you add a half or subtract a half? And it's all about just take a second, draw a quick picture, draw this quick little picture with some bars, figure out if you're, less than or equal to, what's the last bar that you have? If you're strictly less than, what's the last bar you have? If it's greater than or greater than, whatever it is, just figure out what the last bar is that you need to include in your approximation, and then figure out what the endpoint is for that bar, right? If you're doing less than, then you want to find the upper edge of the bar, right? And if you're doing a greater than, then you obviously need to include the lower edge of the bar. And then if you do that, you can always figure out, whether you should be adding or subtracting a half. And I like that better than just trying to memorize these stupid things, because math is not a set of things to be memorized, damn it. Math is a mindset. It's the idea of stop and think through it logically, draw a picture, and use some logic and deduce, oh, in this instance, I add 0.5, and in this instance, I subtract 0.5. And now you've learned to think through something rather than memorizing something that only works in specific instances. All right, so that's the last time I'll get on that soapbox. The last thing we talk about in this module is the central limit theorem. And the central limit theorem basically just means that if you are to run experiments over and over and over again, the experimental will always approach the theory. And the other thing it tells us is that if you have a sample of data and you want to know what's the probability that if I grab 5 things and I want to look at the average of those 5 things and say, what's the probability that that value is above something or below something or whatever, that all that I have to do is take the statistics from my sample and tweak them based on the size of the sample that I'm looking for. And basically what that means is you just have to take your standard deviation and divide by the square root of how many things you're looking at. So for instance, this example, I think will make what I just had a terrible way of explaining. This will make it a lot more clearer. So they say that on average, tires last 20,000 miles and they have a standard deviation of 3,500 miles. So if you go out, so that means all tires, right? This would be the same thing if you, let's say you measured the lifespan of 1,000 tires or 1,000 sets of tires, right? And from that sample of 1,000, you got an average of 20,000 miles and a standard deviation of 3,500. It wouldn't matter if these numbers came from a sample or if they came from a population, right? Because the way this is written, it makes it seem like this is based on all tires, right? That they've looked at tires for a very long time, and on average, they last 20,000 miles with a standard deviation of 3,500 miles. So it kind of sounds like a population thing, but it could also just be from a sample. Now, if you were to go and randomly choose 70 tires from your sample of 1,000 or from the entire population of tires, it doesn't matter, just wherever these values came from, right? So if they came from your sample or if they came from population, it doesn't matter. If you went and randomly chose 70 tires from amongst those tires, you could then ask all of these same probability questions, right? Before, all the probability questions we've had were based on one thing, right? What's the probability I pick one thing and it's less than 14? What's the probability I pick one thing and it's greater than 2? What's the probability I pick one thing and it's in between negative 1.3 and positive 2.2, right? Those are all probabilities of picking one thing, whatever that thing happens to be. Well, what if you don't want to pick 1? What if you want to pick 5? What if you want to pick 20? What if you want to pick 70? Well, the central limit theorem tells you that this normal curve will still work perfectly fine. The only thing you have to do is you have to adjust the standard deviation. And you adjust the standard deviation by taking the standard deviation of the original and dividing by the square root of your sample size. So if you're going to pick 70 tires and figure out the probability that the mean is less than 19,500, well, you use the same mean of 20,000, and the new standard deviation is just 3,500 divided by the square root of 70. You put that into the formula and run it, and it will give you the correct answer. Now, the nice thing about SAS is you don't even have to do this in your calculator, right? And get this answer of 4.1833. You can actually just type in this exact thing and do square root of 70. So for instance, how did it close on me? Oh, it closed on me. Okay, so if we come down here to our normal probability, right? And our mean was 20,000. Sorry, it's here, 20,000. And the value of interest we were interested in was 19,500. So this is 19,500. And the original standard deviation was 3,500. Now, if we run this, this is the probability of picking 1 tire. What's the probability that 1 tire will have a lifespan of 19,500 or less? Because remember, that's what a CDF is always that or less. So we run this. It's hard to see, but there it is, right? 44%. Which makes sense, remember, because if the average is 20,000, 19.5 is just a little to the left of it. And remember, the area under the curve from the average to the left is always 50%. So if we're a little bit to the left of it, and the CDF gives us the area to the left of that, it's going to be a little less than 50%. And that's how we got, 44 point something. Okay, but that's 1 tire. We don't want to do 1 tire. We want to do 70 tires. So if we go back to our code, and all we have to do is change the standard deviation, and instead of doing the math in the calculator and plugging this in, we can literally just do divide by SQR. Is it SQR or SQRT? I think it's SQR. Let me see if it works. All right, I don't like that color. I think it is SQRT. Yep. Okay. See how it changed to blue? So it became the square root function. So now this is actually going to do the math for me. And if I run this without having to put it in the calculator and get that 400 or whatever it was, run it, and there's the answer, 0.116. And look at, there's my standard deviation of 418.33, and look what we had here, 418.33. It does the math for you. So it's pretty cool that you don't even have to slam that into a calculator. Questions?
Oh, that would have been so helpful, like yesterday, before we did it all by hand, right?
Yep. All right. So are we good, guys? I think this should be enough to get you going on the homework, and then we can do some more examples on Thursday.
Is it okay if I ask one quick question about the homework?
No. Yeah, go ahead.
Please. So I feel pretty good about my answers to the homework. On the very last one, it's the toughness one, and you run the normal QQ plot, and you get a correlation coefficient, and you get a p-value. And I've got those,
Yep.
But it says to comment on the degree of fit. Now, I know the correlation coefficient tells me the degree of fit, and I've always thought of the p-value in terms of significance. I guess I don't know how to equate p-value to the degree of fit.
Yeah, there are kind of tables out there that if you look for them, they'll tell you It's one of those things where there's no real hard, fast rule, but there is kind of a general consensus. Basically, what it is any p-value that's greater than 0.5 is considered an excellent fit. Anything that's between 10% and 50% is considered a good fit. Anything that's between 5% and 10% is an acceptable fit. Anything between 1% and 5% is a poor fit, and anything less than 1% is a very poor fit. That's kind of the general consensus. So I think your p-value is greater than 0.5, I remember
It's
correctly.
like 0.75, so it's
yeah.
really good.
Yeah, so it's excellent. Yeah, which makes sense because the R value you get is like 0.96 or 0.98 or something like
Yeah,
that.
it's really good.
Yeah. So that would make sense that it would be a good fit.
Okay.
Or
Yeah, I just
excellent.
always have thought of P's as significant or not significant. And so I'm like, I'm not.
Yeah.
So thank you.
Yeah, it's really, I really hate that they call it a P because it does confuse students with what p-value normally is, which is exactly what you said. It's normally a significance, measurement of significance. Wiley, you got a question?
Yes, I do. I didn't hear the question about doing these by hand. What was the question?
This last one?
No, prior to her.
Oh, somebody said that it would have been so helpful if I had shown you guys how to do this in SAS before, because they had been doing them, I guess, by hand over the weekend.
Okay. I didn't know if we were required to do these by hand.
Oh, God,
or not.
no.
That's why I was asking.
No,
Okay.
great question. No, by all means, technology is there, so use it. I am not a Luddite. You guys don't have to do this stuff by hand.
Okay.
No, that's not to say that somebody teaching 810 won't force you to do something by hand. Who knows? But I would really doubt it. The school really tends to lean heavily on technology. So I don't think anybody's going to require you to do anything by hand. I surely know that unless you have some really archaic jerk on your dissertation committee, nobody's going to ask you to do anything by hand for your dissertation. So you should be fine.
Okay.
Okay. Anything else before we go? All right, we'll end it there. I'll see you guys Wednesday, right? We're meeting Wednesday instead of Thursday. So try and get on the homework as much as you can to get as much of it done as you can so you can have whatever you haven't figured out ready to ask questions about on Wednesday. And of course, the videos are always there from previous weeks, and I pretty much go through damn near every homework question, 1 week or the other. So if you watch all those videos, you should get the answers to, any questions you might have if you don't want to wait till Wednesday or you can't make it Wednesday. Prince, you got one last question?
No, I'm good. Thank
Okay.
you so much.
Thanks, guys. See you Wednesday.
Thank you.